Hey everyone, welcome back to the Plug and Chug series for 16.6, and we're on the second video now where we're talking about vector fields. I'm actually going to have two methods then that I'm going to show you in this video, and it's one of those videos where I show two methods, but they work on the same problem. And so, so let's take a look at the problem then. So again, remember this first video up here, we took a double integral over some scalar function, right? So this guy right here is a scalar function. So what is a scalar function? It just means that you have like a bunch of x's and y's added together, and then it's different from a vector field, right? Because a vector field, you have however many components. So in 3 dimensions, right, you have 3 components, and each one of these guys is a function itself. While in a scalar field, there's only one function that we ever deal with. Okay, so again, that's the difference between that video and then this video we're talking about. We're dealing with vector fields, and so we'll call them big F. We actually usually don't write f of x, y, z, so it's just big F is equal to some vector of functions. So let's take a look then at 16.6, number 42. And so what's the problem? Let me actually pull up the problem so I can read it to you guys. So find the outward flux. Find the outward flux of the field F is equal to xz, yz, comma 1 across the surface of the upper cap cut from the solid sphere x squared plus y squared plus z squared less than or equal to 25 by the plane. What's the plane? Z equals 3. All right. So so when we're talking about vector fields, then when we have F like this, we're going to talk about flux through a surface, okay? And I know we haven't really talked about flux before. I mentioned it briefly in Green's theorem. But what is flux in 3 dimensions, right? So let's draw this region right now because it'll be useful too. So if we draw this region, I have some sphere, right? Okay, and well, okay. I forgot another thing. We also only want the positive. Oh yeah, it's the upper cap, right? So upper cap means the positive guy. So here's my sphere. Terrible sphere, I know. It's okay. And then it gets cut then by a plane. Z equals 3. So Z equals 3 is right here. And then now what I'm left with then is just now I'm just left with the cap up here. All right, and then so Z equals 3 is this plane in red. Z equals 3. And remember, when you're cut by something, there's no lid here, right? There's no lid down here. Meanwhile, up here, we have the surface in blue that's shaded in, right? So there's no lid on this cap, but so what is flux then? Flux just means here's my vector field F. All right, so at every point, my vector field is like some kind of has some kind of directionality to it, and essentially, I want to see like how much vector field goes through this cap right here. All right. So that's what I'm trying to find. I'm trying to find how much vector field goes through this blue guy. Remember, it can enter through, it can pass through the open guy here. All right, the cap here is open. Even if it were not open, it would still be able to pass through, but that's a different story. But you can think of it then as, because this guy down here is empty, we don't have to worry about calculating the flux through this cap or the lid, and we only have to worry about the flux through the shaded blue part, which is the cap. All right, so that's the pro then of not having a lid, but you'll see it actually ends up being a con later on in like 16.8. But anyways, so that's what we're dealing with. And there are two ways to approach this problem right here. All right? There are two ways to approach 14.2. And I'll show you both ways. The first way is to parameterize. Okay, and so what I want to do then is I want to parameterize my region up here. I want to parameterize this region. And how do I do that? Well, it looks like I should probably do it in spherical coordinates, right? So, so what is it? Well, this is okay. So let's say S then of phi and theta, right? This is the spherical coordinate parameterization, is equal to, okay. Well, in spherical coordinates, right, x is equal to rho rho sine phi cos theta, right, and then y is equal to rho sine phi sine theta, and then z is equal to rho cos phi, right? And so now what we want to do then is, okay, what is rho, right? Because we can figure out rho. And since my region is going to be like part of a sphere, right, then everywhere on this blue guy, right, every point on this blue shaded surface here, I'm going to be the same distance from the origin, right? And that distance is going to be 5 from 25. So for example, if I'm this green point right here, my distance to the origin is going to be the same if I were like here to the origin, right? So that's going to be the same distance no matter where I am on the blue part, the cap. So rho is going to be 5, and so then I'm going to have 5 sine phi cos theta, 5 sine phi sine theta, and then 5 cos phi. Okay, and now what? Okay, now I have to figure out what my bounds are on this guy, right? Because I need to figure out now the bounds on phi and theta. And so let's deal with theta first. Well, if you look at this region, right, well, first of all, in this problem, there's no restrictions in the xy plane, which is where we see theta. And so I've repeated myself on this a lot. So if there's no restrictions in the xy plane, then theta is just going to go from 0 to 2 pi. Okay? All right. Phi, on the other hand, this is a little harder. So phi, right, phi is the angle from the z-axis. So essentially, I need to find then, right, so if phi is really, right, like that angle right here. So I need to find what the upper bound of phi is. Well, the lower bound is obviously 0 because my region is in the my region is defined on the z-axis right here, right? So that means the lower bound then is going to be 0 for phi. But what is the upper bound for phi? Well, the upper bound for phi comes like right here, right, where my cap gets cut off by the z-plane. And so what is this angle here then? Okay, and for this problem, it doesn't seem too nice. So remember, let's then just draw the cross section in the zy plane because that's all we have to do to look at phi. So here's y and here's z. So phi up here, right? Here's my cap, and then I'm cut off by the point. Cut off by this point, this line y equals 3, z equals 3, right? That's the plane z equals 3. And, okay, well, that means this distance here is 3, right, if z is equal to 3. All right, and I know what the distance from the origin to any point on the sphere is. It's going to be 5. And so, well, from there, I can deduce then by the Pythagorean theorem, right, that this line from the z-axis to this point right here is going to be 4. And now I need to find what the heck this angle phi is right here. And as you can tell, it's not the greatest, right? Because it's really, well, I know what sine of phi is, right? I know sine of phi is opposite over hypotenuse, so it's 4/5, right? So I know sine phi is equal to 4/5. I know what cosine phi is. Cosine phi is 3/5. Okay. Cosine phi is 3/5, and I know what tangent phi is, right? Tangent phi is going to be opposite over adjacent, so that's going to be 4/3. So Yeah, so what is phi? Well, then phi is equal to, in this first case, it's equal to like arc sine 4/5, or it's equal to arc cosine 3/5, or it's equal to arc tangent 4/3. So there's really no good thing to put for phi, right? I can't. It's not like some pi over 6 or something like that. So for now, let's just say it's like arc sine 4/5 or it's arc cosine 3/5. It's one of these two. Okay, so we don't really have to worry about this until we start doing the integral. But this is going to be my parameterization. All right. So again, these two are equal to each other, so you can choose either this top one or this bottom one. It doesn't matter. But I'm just going to keep them both for now because, as we'll see, it actually ends up mattering. Okay, so now we parameterize our surface, which took forever. And now what do we want to do? Well, according to the textbook, then the flux across a surface, flux across a parameterized surface is the following. Surface is the double integral of s of f dot n d sigma, right? So this is what we're calculating. This is flux, right? So when you're asked to find the flux, this is flux over a surface, all right? Flux over a surface S is equal to the double integral of f dotted with ru cross rv du dv. So what do I have here then? And over the region in the UV plane. So what do I have here? Well, this means so RU cross RV is just a parameterized is just a parameterization, right? And then the partials, and then you got F, which needs to be dotted with these guys. So okay, then let's find in our case, right? Okay, so in our case, what is F? Well, F was equal to, if we remember from up here, F was equal to xz, yz, and 1, right? So F was equal to xz, yz, and 1, all right? But remember, but look, we're integrating it in terms of u and v. So in our case, we're going to integrate in terms of theta and phi, right? So we can't have x's and z's. And so what I have to do then is I have to go up to my parameterization right here, right? I have to go to this parameterization, and I have to substitute in this guy for x, this guy for y, and this guy for z. Okay, so let's do that real quick then. Then what does this become? This becomes 5 sine phi cosine phi times 5 cosine phi. So then that's like 25 sine phi cosine phi cosine theta, right? And then the next guy is yz. So yz, I got to multiply those guys, and that's like 25 sine phi cosine phi cosine theta, and then 1. Okay. Alrighty. And now what? Or I did something wrong here. This guy should be sine theta. My bad. I just copied the same guy down twice. Whoops. Okay, so that's F. And now I need to find RU cross RV, right? So in our case, that's SR cross S theta. But, you know, let's find S or S phi cross S theta. So let's find S sub phi first. Right? Remember, U and V are just placeholders for whatever you're parameterizing with respect to. And since we're doing phi and theta, got to take the partial with respect to those. So S phi, all right, is going to be equal to, I have it here somewhere. It's equal to 5 cosine phi, cosine theta, comma, 5 cosine phi, 5 sine theta, comma, negative 5 sine theta. All right, and and S theta is equal to negative 5 sine phi sine theta. All right, negative 5 sine phi sine theta, comma, 5 sine phi cosine theta, comma, 0. Okay, and now what? Now I got to do S phi cross S theta. Okay, and what is this equal to? This is equal to, IJK. All right, And now I have 5 cos phi cos theta, 5 cos phi sine theta. I don't know what this extra 5 is doing there, my bad. And cos phi sine theta, okay, and then -5 sine theta, sine phi. Woof. And then this is -5 sine phi sine theta, 5 sine phi cos theta, 0. Okay. And now I gotta take the cross product, and so I get 5 cos theta, 5 cos phi, or 25 cos phi cos, 25 cos phi sine phi cos squared, right? So it's 25 cos phi sine phi cos squared, and then I get plus 25 cos phi sine phi sine squared. And so essentially you can factor out then 25 cos phi sine phi, and so then you get cosine squared plus sine squared, so then this becomes 25 cos phi sine phi. Okay. Oh wow, that's the k component. Whoops. Okay, so that's the k component. Whoops, I did a k component first. That happens. So 25 cos phi sine phi, right? Because in order to get these guys, these two blue lines multiplying each other, I gotta cross out the k. Yeah, so whoops, I did that backwards, but it's okay. That's correct. Now what? Now let's find then what I should be, and that gets me 0, and then this is 25 sine squared phi cos theta. All right, and then for j, you should get then 25 sine squared phi sine theta. Okie ducks. And now what? So this actually, you need to be very careful here, because look, I just by chance, right? By chance, I said, oh, let phi be first and theta be second. So what if I had theta first and phi second, right? That doesn't change anything. And so if here I had s theta cross s phi, right? Remember how this is different when we swap the vectors in a cross product. It becomes a negative vector, right? It becomes normal in the other way. So I need to be very careful. I need to make sure that what I have here, I need to make sure this is the correct normal. Okay, and how do I do that? How do I make sure that this is going to be the correct normal? Well, okay. Essentially, one way to do this then is, remember, let's go to the sketch back here, right? And we want to find the outer, the flux of the field across the surface. And I might have skipped some words here real quick. Let me just read this. Find the outward flux. Yeah, it is the outward flux, right? So it's outward flux, and it's almost always going to say outward. Like, it will always be the outward flux. And what do I mean by outward flux then? It means that the normal at any point on the surface, right? So I know this is super shaded in blue, but okay. So imagine I'm at this point on the surface then. I want the normal pointing outward, all right? I don't want it pointing inside my cap. I want it pointed outward. So here, like, I want to point it outward. And you'll notice then that at every point in the surface, right, what is true about the outward pointing normal? The z component is positive, right? If you look at every single one of these vectors that I just drew on the surface, the outward pointing normal has a positive z. So that means I want to make sure that this guy here, this z value is going to be positive. And I know it's going to be positive because if we look at the sketch here, right, phi never leaves the first quadrant. You can think of it that way, where every value that phi can take on, right? So every like cosine phi and sine phi, right? Because I'm worried about cosine phi, sine phi. Every value of cosine phi, sine phi in this quadrant right here has to be positive, because both z and both y are positive there, right? Oops. So both z and both y's are positive in this quadrant, and since I'm only like relegated to this area right here, cosine phi, sine phi are going to be positive. So this is the correct normal, because this guy is always bigger than 0. And so yeah, so we're good. Okay. Um, otherwise, if you did s theta cross s phi, you would get negative, 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 and then you would need to take the normal that points in the positive z direction, and then you need to just multiply this entire thing through by -1. Again, that's if you had s theta cross s phi, the opposite of what we have right now. Okay. But anyways, so right now we actually have this correct. So that's good. And now what I need to do then is I need to do this integral, right? I need to do the double integral of what to have f dot ru cross rv. So f is up here. It's 25 sine phi cos theta, 25 sine phi cos sine theta 1. Okay, and I need to dot it with 25 sine squared phi cos theta, 25 sine squared phi sine theta, and then 25 cos phi sine phi. Oof. All right. And then now I need like d phi d theta, right? And what are my bounds? So let's not worry about that for now. But let's actually calculate this cross product out, and so this dot product. I mean, so this then becomes a massive clusterfuck. But essentially, what happens is, right, you get a sine square term by dotting this the y guys, and here you get a cosine square term by dotting the x guys. All right, and so what happens then is we escape with 625 sine phi, sine cubed phi cos phi, and then this last one is plus 25 cos phi sine phi. And so this first guy comes from this dot this plus this dot that. All right. Try it out yourself. Work it out yourself. It's just algebra. I know that's correct. And then now what? Now we need to integrate this guy. Right. And our bounds then were from 0. So d phi d theta. Hopefully that's what I chose here. It is. Okay, good. So theta was 0 to 2 pi. Okay, that's fine. And remember, phi was 0, and then we had this wonky shit right here, right, where I chose arc sine or arc cosine. For now, I'm going to put arc sine 4/5 or arc cosine or arc cosine 3/5. So it's really wonky, but let's see what happens. How do I integrate this guy? It looks like I do a u sub, right? And a u sub for what? I do a u sub for sine phi, right? Because I got these single cosines just hanging out. So if I do a u sub, let's do a different color. U is equal to sine phi, then du is equal to cosine phi, right? And okay, so what does this become? Then this becomes well, that's fine, and then that, we'll deal with that bound later. But then this becomes 625 u cubed plus 25u, right? d phi d theta, and that's because if you factor out this cosine phi, right, from here, and then you get this times cosine phi, and then, right, what does cosine phi d phi become? Well, cosine phi d phi is du, so then this guy gets replaced by du. All right, good. And, okay, and now what? Since u equals sine phi, then the lower bound is going to become sine of 0, which is still 0, and the upper bound is going to become sine of arc sine 4/5 or arc cosine 3/5. Well, it's really obvious which one we want now, right? Because I need to take the sine. So if I take the sine of arc sine, right? Remember, arc sine is just sine inverse. So sine of sine inverse, they cancel each other. And so I'm just left with 4/5 as my upper bound, right? Because I'm taking the sine of either this guy or that guy, and there's no reason why I would take the sine of arc cosine. That doesn't make any sense. But if I take the sine of arc sine, right, sine of arc sine 4/5 is equal to sine inverse, sine times like sine of sine inverse of 4/5. So that's just equal to 4/5. Right, because arc sine is sine inverse. So yeah, I mean, now we get this integral, And we can do that integral, right? This integral is like, it looks bad, but at least we can do it. And yeah, and if you do it out, you should get, let's just finish this. I'm actually going to make a separate video because this one's running really long. But what do you get? You get 625 over 4 u to the fourth plus 25 over 2 u squared, all right, d theta. And then, of course, this guy has to be evaluated from 0 to 4/5. Okay, and now what do you get? So you get then 0 to 2 pi. This becomes 625 over 4 times 4/5 to the fourth, which is really 256. Wait, 4/5. Yeah, so 256 over 5 to the fourth is 625. All right. Hey, that looks promising. And then plus 25 over 2 times 16 over 25. All right, and then that's times d theta. And what is this? Well, right, you get a lot of canceling going on. Cancel, 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 cancel. This guy becomes 64. Cancel, 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 cancel. You get an 8. And so really, you just got the integral from 0 to 2 pi of 64 plus 8 d theta. So that's then 72 times 2 pi, which is 144 pi, which is the correct answer to this problem. So the amount of vector field going through this cap, which is what we're trying to find, is 144 pi. Okay? And so that's how you do it. And you notice this was a pain in the ass, right? This took so long to do. What can I say? This is just a setup for a shortcut in 16.8. So we'll find an easier way to do this problem in 16.8. It does involve, in 16.8, it does involve a better understanding of these problems. It does involve a more conceptual understanding, but I do think it'll be a little easier in 16.8. And what else? I don't know if I want to show the other way to do this problem. You know what? I think I will. So that'll be the next video, and then we'll move on to Stokes' theorem. So I'll see you guys one more video in 16.6. Don't know if it will be an addendum or not, but it's going to be the same problem. We're just going to do it a different way without the parameterizing. And I don't know if it's going to be a little easier. I think it will be a little easier, but it's a special case why we can do it then. So I'll see you guys in that video.